polynomial. So what is it? Well, consider the function e to the x. What is the value of f at 0.1, which is e to the 0.1, and we don't know, okay? We can, if we had a calculator, fine, but if we can't find the exact value, is there a way to approximate the value without a technology, without a calculator? Because remember, back in the day, they didn't have calculators, so they had to figure out a way to do this without one. We learned earlier that we can use the tangent line to approximate a value of a function at a point. Okay, so this is what I'm illustrating right here. The function is e to the x, the derivative is e to the x. The point would be plug in 0, you get 1. The derivative, plug in 0, you get 1. So the tangent line at 0 would be y equals 1 plus x. So we can approximate the value of this function right there. And we can use this, okay, to kind of like approximate this number, because this number right here is very close to 0. Okay? So let's look at even further. Consider this. So the center, this is where we want to our polynomial to match the function, the point where they are equal. Our polynomial is centered at or expanded about x equals 0, the point of tangency. When c equals 0, the Taylor polynomial is also called the Maclaurin polynomial. Okay, so when it's at 0, it has a special name. It's either called Maclaurin or Taylor. It's the same thing. Degree, the highest exponent on a term in the Taylor polynomial. Our Taylor polynomial, p sub 1 of x, this is a first degree Taylor polynomial. Okay, because n is equal to 1. Notation. They usually use p, but they sometimes will, so you'll see books will use t for Taylor, p for polynomial, so they can use either one of those two. They can call it whatever they want, technically, but these are the most common ones that are used. The equation, we write the terms of a Taylor polynomial in ascending order. So the first term is like the constant, and then all the way up to the highest exponent, so it's a little bit different from a normal polynomial standard form. Centered at 0 would be this one. If I want it centered at another value, then the Taylor polynomial takes on this form right here, where you just have x minus that other value. Other than that, it's very identical to what you're going to be dealing with. All right, let's continue our exploration of our e to the x and our Taylor polynomial 1 plus x. All right, so let's take a look at it. I'm going to show it to you so here you can see it. I got to zoom out just a bit so you can see it all. All right, so here's our e to the x graph that I've drawn. Here is our 0, 1, and here's our tangent line, 1 plus x. For values near 0, our polynomial is a good approximation. Okay, our polynomial, our 1 plus x at 0.1 is 1.1. For the actual function, e to the 0.1, it's 1.105, so it's pretty darn close. But for values that are farther from 0, the farther I get from 0, you can see that the approximation isn't very good. At even just a little ways out, so if I plug in 4, this is going to give me a 5, but the actual function at 4 is 54.598. So not a good approximation at all. So the question then comes is, well, how do I make it better? Okay, what do I do now? How do I get better approximations, which is what I'm saying right here. To get a better approximations for this function, we want to find additional characteristics for our polynomial to share with f of x at 0. We are essentially trying to clone the function. The more derivatives we match, the better our clone is for the function. So if I take the derivative, then they share the same slope. If I take the second derivative, they share the same concavity at that point, and so forth and so on. The higher and higher derivatives that we take, the more derivatives we match, the better our approximation is going to be around that point. So I have an example here we're going to look at using our same problem. Let me get my paper over here. We want to find a second degree Taylor polynomial centered at 0 for e to the x. Okay, so let's take a look at this and walk through this process. of what's happening. All right, so the first thing we want to do is we want to find what does a second degree Taylor polynomial look like. Okay, what does it look like? Well, it is the second of x. So we'll have an a sub 0, we'll have an a1x, and an a sub 2x squared. So this is the general form for this. We want to match the points. Okay, so what is p sub 2 at 0? That is going to be f of 0, which is e to the 0, which is 1. So if I match these things, I want this to match that. Okay, and so then when I plug in 0, I should get 1. This tells me then that a sub 0 equals 1. So that's how I get that value. So let's match slope. So we want our Taylor polynomial's derivative at 0 to match the f prime at 0. Okay? Well, what is the second derivative? Well, take the derivative of this. That's a constant. That'll be 0. This turns into a 1, so I basically get, so p2 prime at x is going to be a sub 1 plus 2a squared x. So if I plug in 0, you can see that this right here is going to go to 0, and I simply just get a sub 1. So what is the derivative of f of x? Well, it's going to be e to the x. And what is f prime at 0? Well, that's e to the 0, which is 1. So combining these things, we want these to be equal. Then I just found out that a sub 1 has to be 1. And then keep on going. Match the second derivatives. We want them to be 0. We want them to be equal. We want them to be equal. So what is the second derivative of our polynomial? Well, that's going to be gone. Take the derivative of this. That's gone because it's constant. I have 2 times this, so it's going to be 2a sub 2. So what is that at 0? No, it's just the same thing. Okay. Over here we have f double prime at x is going to be e to the x, and f double prime at 0 is still 1. So then I only know 2a sub 2 wants to be 1, so a sub 2 has to be 1/2. Now, so now that I know what each one of these 3 coefficients are, I can come over here and write my Taylor polynomial, a second degree Taylor polynomial. And there you go. Okay? So I went and I graphed it, kind of show you how it looks as you keep on going, and how much better this solution is to the first one, and how it matches a little bit more. Let me move this out of the way here and show you. So here is the problem we just did. Okay, if you look right here, here's the e to the x graph right there. Here's the first one, 1 plus x. And now I have the other one, which now matches a quadratic. See this? And see how it gets, it's a little bit better approximation. Okay, it's a lot closer for a lot longer. Okay, and if I want to get even more, I just keep building a bigger and bigger Taylor polynomial around it. So how do I do that? What is a process I can follow that will help me? So let's look at that process and see what we can come up with. So how do I build a Taylor polynomial? So consider this polynomial all the way out here. This is the one centered around c. We need to match up traits of our polynomial with those of the function f of x. We need to find all of these derivatives and match them up to a polynomial. Okay? And so for f at c, okay, what is the polynomial at c? If I plug in c, you can see that everything here is going to be 0. And the only thing left here is a sub 0. So f of c is a sub 0. Okay, so we're building up what these values are. And if I continue this process looking for a pattern, okay, just keep this process going. Let me show you right here. We have this right here. Take the derivative. If I take the derivative of this thing, I get all this. And I can see that the first derivative at c is a sub 1. Keep on going. Just follow the math. See, I didn't multiply things out. I'm just doing it as a products here. If I do that, then the pattern continues. The second derivative at c is going to be 2a sub 2. That means a sub 2 is going to be the second derivative at c over 2. There's that 1/2 we found in the other one. If I keep on going, what happens? If I keep going, then these right here become a number, 3 times 2. And if the pattern continues even more, and if I keep on going, you'll notice that I'm getting what here is a factorial. For every derivative that keeps on going all the way out to n, this is just n times n minus 1 times n minus 2 all the way down to 1. And so then a sub n is going to be the nth derivative at c divided by n factorial. And so that's where these terms come from. And since we know that, we can bypass going through a lot of stuff and just simply go focusing on the derivative at a value. Okay, so here is our Taylor polynomial centered at c. Okay, and you see that each term is f of c, f prime at c, f double prime at c over 2 factorial, the third derivative over 3 factorial, and so forth and so on. And if it was centered at 0 or Maclaurin polynomial, these would be 0 values in here, and there would be x minus 0, which is just this right here. Okay, so this is how you would find, this is your formula for Taylor polynomials that we're going to be using. So with that, I'm going to do another example for you, which is right here. I'm going to do it over on this paper, and we'll walk through a problem. The function f has derivatives of all orders for all real values of x. Selected values of f and its derivatives at x equals 2 are given in the table. Write an equation of the third degree Taylor polynomial for f of x at x equals 2. Okay, so based off of our formula, we want to find a couple of things as we do this work. What is n going to be, and what is c going to be? We're centered around 2, and n is going to be 3 because we want a third degree Taylor polynomial. So our p of 3 is going to be f of 2, f prime at 2 times x minus 2, f double prime at 2, x minus 2 squared over 2 factorial, and then the third derivative at 2 over 3 factorial, x minus 2 cubed. So all I have to do is find these derivatives at those values, and I have my answer. Okay, so do I know the value of the function at 2? Here's the function. X is equal to 2. The value of the function is negative 3. F prime at 2 is 1. And that'll be times x minus 2. The second derivative at 2 is 0. So this will be 0 over 2 factorial x minus 2 squared. And then this is 7 over 3 factorial x minus 2 cubed. So that's plugging the numbers into our formula, and then just clean it all up and give me my final answer. Negative 3 plus x minus 2 plus 7 over 3 factorial x minus 2 cubed. And there you go. Okay, so that formula, you definitely want to make sure you know this formula. You need to memorize this formula. It's also going to be, in a future work here, it's going to be when we turn this into a Taylor series. This is just going to continue on this pattern for infinity. So this is another reason why you want to make sure you remember this format. Okay? Let's look at another examples that I have. I got 2 more examples for this video. So here's the next one. Find a second degree Taylor polynomial centered at x equals pi over 2 for g of x, which equals sine of x. Okay? So, things that you need to remember, or you need to be told in the problem. You got to know the degree that you're going to be looking for, second degree. You got to know where you're centered at. You're centered at pi over 2. And we have to know what the function is, which is sine of x. So we have to know those 3 things to do this work. Then you can come over here and write out your generic form based off of the formula that we had. We want a second degree Taylor polynomial. It's going to be the function at the point plus the derivative of the function at the point times x minus the point, and then the second derivative at the point divided by 2 factorial x minus pi over 2 squared. And because I want a second degree, we stop there. So we need to find these values right here. So to do that, what is g of x? Well, it's the sine of x. What is g prime of x? Derivative of sine is the cosine. What is g double prime of x? Well, derivative of cosine is minus the sine. So for each of these, we're going to find out pi over 2. The sine of pi over 2, 1. The cosine of pi over 2, 0. The sine of pi over 2 is 1, but then there's a minus in front, so this is going to be negative 1. So with those values and our template right here, our second degree Taylor polynomials for this function is going to be 1, then negative 1 over 2 factorial x minus pi over 2 squared. Okay? And you can leave it like that. You can simplify it out more if you wanted to, but we're just going to leave it like that for now. Okay? And then here's our last example that I have. How to find some things in different formats. So I'm giving you this picture over here. I got a shaded region over here. That's area is 67 over 8. A portion of the graph of f along the tangent line of f at 2 is shown. The region bounded by the graph of f and the x-axis between 2 and 5 is shaded in the figure. H is this integration of f of t, antiderivative of this, from 5 to x. Find a second degree Taylor polynomial for h centered at 2. So again, identify I want a second degree and I'm centered at 2. So for h, for this Taylor polynomial, I need h of 2, h prime at 2 times x minus 2, and then h double prime at 2 over 2 factorial x minus 2 squared. That's what I need. So I have to find these three things. So h of 2 is the integration of 5 to 2 of f of t dt. Switching the limits around gives me a negative 67 over 8. From 2 to 5, it's positive. From 5 to 2 would be negative. So there you go. What is h prime at 2? Well, that's the derivative with respect to x of this function. So fundamental theorem of calculus says that I'm going to get simply this thing right here plugged in here is going to be f of x, and we want to evaluate this at x equals 2. So what is f of 2? It is 3. 3. And so what is h double prime? Well, that'll be f prime at 2. And so what is the slope of this line right here? Knowing that it goes to this point right here at 0, 2, then I can just do a secant slope, or the slope of that tangent line there, 3 minus 2, 2 minus 0, 1/2. And so then I can just come down here and write my Taylor polynomial now. So you can see that if you do these problems like this, know what you're looking for, and that gives you focus on where to go for it, okay? I just needed to find these three values. The rest are just part of the formula itself. Okay? If you have any questions, make sure you bring them up to me, and that ends this video.